Do you know if the buses are running? Any update? Anybody knows?
Not yet, sir.
Okay, so we will start. So we'll continue where we left off yesterday. So we will, last few lectures we've been looking at maximum likelihood estimation. So if you remember in the beginning when we started talking about maximum likelihood, I also mentioned there is another type of estimate called MAP. Let me see if. Okay, so let us see this. See again, let's just revise what we just did. So we were looking at maximum likelihood estimation of parameters. Okay, so and how did we use it for classification? We said if P of Ci given feature vector is by Bayes rule V of x given Ci into P of Ci, and that we said was equivalent to P of x given theta ml into P of Ci. So PSCI is reasonably easy to compute. Either somebody gives you this information or we can estimate it as a proportion of the number of training examples per class. And this one is the estimation of the parameters given the data, which is the maximum likelihood estimate. And I should write theta IML. Let's see. Theta I ML. This is the ML estimation of the ith class, the parameters of the ith class, because it is Ci, conditioned on Ci. So, and we also found out how to estimate this P of, no, what is this? We said the theta IML was nothing but the R max over theta P of D given theta, where D is the data set. Yeah, data set of class I, because I'm keeping on forgetting the I. Okay. Okay, so this is how we estimated the theta i's, right? So now come back again. So look at this step. What is happening here? What is happening here? Somebody tell me. Ashish Rana, are you there?
Yes, sir.
Yeah, can you tell me what's happening in this equation? R max over theta, P of di given theta. What is happening here?
Sir, we are trying to find the maximum theta, like the parameter of.
No, let me tell you how will you implement this. For example, suppose you're writing an algorithm, or suppose you're writing a program to do this step. How will you do this step?
Sir, as per like what we have studied, like sir,
Hmm.
we'll find sir like a p d given theta will form a like for example, it is forming a normal distribution
It
kind
is
of sir.
what? Sorry.
It is forming a sir function like a curve kind of thing, sir. So we'll find the maximum the maximum point where P d given theta is maximum for a given parameter theta set. That's how we'll find it.
Yeah, that is that I agree. But how will you implement this in practice?
Okay, sir.
How will you implement this in practice?
Let me think about it.
Anyway, we have done this by the way which we did it was we differentiated this with respect to theta and
Right.
equated it to 0. But
Right.
that can give me a local maximum.
Right.
So to be really sure that if you have got a global maximum, yeah, you can mute Ashish. So you to be really sure if you have a global maximum, you should actually look at the entire theta space. Right, the entire theta space has to be searched. Only then we can be sure that we will be getting a global maximum. But see, let's again take the same example which we started with. Height and weight. Okay, so I'll tell you. I'll explain to you what I mean by this. So let me say now this is let's say weight, and this is height. Okay, so now let's say the height and weight of the children are here, and adults are, let's say, maybe here. So okay, let me see. There is some ellipse. Sorry, it's a bad ellipse, but let me bring this a little closer. This is, yeah, let's say. So this is the distribution, and let's say this is adult, and this is child. I've just drawn the class conditional densities of adults and children. Okay, assume that they are nice ellipses. Now, let's say this is, let's say, one population. Let's say now we do this in the Netherlands. Netherlands, maybe the children have more height. Weight might not vary too much. Let's say I give them children height like this. And maybe adults are more taller than Indians. Okay, so this is Dutch. And this is Indian. Okay, so there is definitely a distribution change, right? Because the population is different. Dutchmen are usually taller, right? So, so suppose you knew this beforehand. You already know what classes you are looking at. So suppose now, if you look at how this maximum likelihood theta, this theta is getting estimated, let's say for Indian children. Okay, so currently we are looking at classification of Indian children and in Indian adults. There are two separate systems. One system is there for Indian adults and Indian children. Another system is there for Dutch children and Dutch adults. So right now we are designing the Indian system. So if you see this theta ml, you have to search the entire theta space. So it makes more sense for you to give a reasonable estimate for the weight for Indian children so this estimate of weight and this estimate of height for Indian children are more reasonable than values over here. This now is not really very relevant for Indian children. Right? Similarly, this kind of weights are also not very relevant for Indian children because you cannot have a weight of 100 kilos. Right? So, whereas maximum likelihood is going to search all of these parameter spaces, all of these spaces it will search. So it's like ML will search this this kind of entire grid, this big grid it's going to search, or even more than that. Actually, it will search the entire XY plane. Okay, but it makes sense for you to search maybe a smaller area. Maybe this much is only enough for children. So basically, what I'm trying to say is that not all values of theta are relevant in most cases. So instead of this maximum likelihood estimate, we will look at another estimate called the map estimate, which takes this into account. Okay, so let me write that down here. This is maximum a posteriori. Posteriori. It is still a point estimate of theta, but it slightly does it in a slightly different way by putting appropriate priors. Okay, so now let us assume, again, let us look at the univariate case. So let us assume P of x given theta is normally distributed with mean mu and variance sigma square. We assume this is known. Now we need to now estimate out of these two parameters, one of them assume it is known. So now we need to find out the mu, the estimate for the mu. You know how to find mu ml. That is what we've been looking at so far. We find the likelihood and it differentiate that with respect to mu. Then that will give you the where it becomes 0, that will give you the mu ml. But now what we are going to do is let's find out P of mu given data. So let's apply Bayes rule. P of data given mu into P of mu by P of d. Okay. We are going to estimate mu. So now, so what is this? This is P of mu given d. This is basically what we want to estimate, and we are going to use this P of and wait. So what we call map estimate is, let's say mu hat map is max P of mu given d. The mu that gives the maximum posterior. So this is the difference, because in the maximum likelihood case, we were looking at, in the ML case, we were looking at only this term, P of d given mu, because that was essentially your likelihood function. We were not putting the prior over the mu, because that is what we want to do here. We want to say that these mu's or these values of height and weight are more likely than these weights. So we want to put a prior distribution on the parameters. Did you understand? We want to put a prior distribution on the parameters, and then we want to give more emphasis to the more likely parameters. So that is the main difference between ML and MAP. ML is only a likelihood estimate, whereas MAP is a posteriori estimate, maximum posteriori estimate. And this is equivalent to log of P D given mu into PF mu by just applying Bayes rule. And what is this? We already know P of D given mu. We already know this. This will be I equal to 1 to n. These are the n data sets. P of xn given mu. And so this is what we were computing in for mu ml. This is what we computed. We maximized this. So now so this term we know how to do, how to handle this term we know. This we can get this P of D given mu we can get by this, by just factorizing out the factorizing and taking the product of the joint densities. And what about P mu? What is the form for the P of mu? That is the prior distribution that we are going to assume some parametric form. And these form the hyperparameters. So who tells you the hyperparameters? Somebody has to tell you. Okay, or you must have some other method to estimate these hyperparameters, but these are assumed to be known, or these are assumed to be that it is assumed that you are able to calculate these. So finally, the posterior becomes P of mu given D becomes I equals 1 to n P of xn given mu into n mu naught sigma naught square by P of D. This is what we are going to estimate. Is it clear? Any questions? Is it clear?
Yes, sir.
Okay. Anyway, even if you guys are zombies, I have to say something. Otherwise, we will end up covering like very less topics. So let me. It doesn't matter whether you speak or not. So let us now try to derive an expression for the map estimate in the same lines of how we did it for the ML case. So let us compute now again we will compute the likelihood of particular mu is equal to log of pi n is equal to 1 to n P of xn given mu into P of mu So now, since we have assumed normal form, we are assuming that x given theta is normally distributed with an unknown mu and a known sigma square. And we also know that the mu's are distributed according to a known mu naught and a known sigma naught square. So we can apply those two results here. So if you take out the so after you apply the log, what do we get? We will get minus, so I'm just writing out the likelihood, minus half n goes to 1 to n xn minus mu by sigma square the whole square minus half mu minus mu naught by sigma naught square, this the whole square. Okay, so the summation is only for this because this represents the likelihood of the entire data and this represents the prior of mu. So there is only one mu, right? It is a the mu's are so we need to estimate only there is only one hyperparameter. There is no, we don't have many observations of mu. We have only one mu which is distributed along distributed according to mu naught sigma naught square. So the summation is only for this. Which will give me, okay, so this is what we have. And now we will apply the same estimate, except that now we have an additional term. So now we are going to find out derivative of this likelihood with respect to mu of L will give me n equal to 1 to n. So I'm going to differentiate this with respect to mu. So this will become xn minus mu, this whole square, right, will become 2 into xn minus mu into multiplied by minus 1 because this is minus mu. And here also this will become mu minus mu naught, 2 into mu minus mu naught, 2 into mu minus mu naught, that's all. And that 2 and this half will go in both the terms. So I get n minus mu the whole square minus mu minus mu naught by sigma naught square, and this I equated to 0. Okay. Now this will give me yeah, I think just do some rearranging. I will say this gives n equal to 1 to n xn minus mu by sigma square is equal to mu minus mu naught by sigma naught square. So what can I do here? Okay, I can split all the summations. Minus n equal to 1 to n mu minus sigma square minus mu. So I'm bringing all the mu's to one side. Okay, mu by mu naught square is equal to minus mu this whole square is equal to minus xn by sigma square minus mu naught by sigma naught square. Bring all mu to the LHS. Okay, so what did I do? This mu and sigma square is here. This mu will become negative. This xn goes here, negative. N equals 1 to n. Okay, so now if you just do some rearranging, finally you will get n mu by sigma square plus mu by sigma naught square is equal to 1 by sigma square and goes from 1 to n xn plus mu naught by sigma square, sigma naught square. What did I do? I did some rearrangement. So this will give me n. This summation is n mu by sigma square plus mu by sigma naught square. And this is, what did I do? Okay, I've removed all the minus signs and I've got xn. This is the same thing. Okay. And finally, I get what if I the mu is equal to, let's call the mu map is equal to mu naught by sigma naught square plus 1 by sigma square xn whole divided by n by sigma square plus 1 by sigma naught square and goes from 1 to n. So what is it? It is mu naught mu naught by mu naught by this term plus 1 by sigma square xn divided by the, I think if you take LCM you'll get this term, and this is, so you can compare it with the mu ml. What was the mu ml? Mu ml was only the sample mean. Okay, so I'll just try to write this in terms of what we already knew. It is nothing but mu naught by sigma naught square plus n by sigma square mu ml, because if I do n into this term is nothing but your sample mean. So sum of the terms is equal to n multiplied by the sample mean, and that was the mu ml. So that is what I've written here, and these terms remain as such by n by sigma square plus 1 by sigma naught square. So you can compare the ML estimate, which is equal to mu ML. So you can see how much the map estimate is different from the ML estimate. So there are some certain additional factors which come here, and the ML estimate is modified with those additional terms. Okay, is this clear? Yeah. So this is so rather than the simple ML, there are some additional terms which come here, which make use of the hyperparameters, which make use of the mu naught and the sigma naught and the mu naught. So you should you can also look at a couple of special cases. For example, if mu naught by mu square is very much greater than 1, okay, then what happens? Map will be mu naught let me just write the whole thing again. Say sigma naught square and what did I do? Okay, so I'm going to multiply and okay, let me write this once again. Let's multiply and divide by sigma square. Okay, then mu map becomes multiply and divide by sigma square. I will get mu naught into sigma square by sigma naught plus I'm multiplying by sigma square. So this will become n mu L by n plus sigma square by sigma naught square. Okay, I've just multiplied and divided by sigma square. So now mu map becomes like this, and this term and this term will be equal to 0. Why? Because sigma naught square by sigma 1 square is much greater than 1. So its reciprocal will be very small. So in this case, I will get mu map is equal to mu ML. So basically what is it saying? It is saying that if the hyperparameter of the variance of the if the variance of the mu which we want to estimate, if there is a very large, if all possible mu's are quite likely, then basically your map estimate will become similar to the maximum likelihood estimate. Only if for certain values of mu there is a peak, that is there is the variance is very, let's say, much smaller. Okay, so only if some values of mu are very likely, only then will you get a significantly different value for the map estimate. Another case, if n becomes infinity, That is, if you have lots of samples, then what will you get? You will again get 1 by n sigma naught square. What is this? See this expression again. I'm multiplying again by. Okay, so I will get 1 by n sigma naught square mu naught plus 1 by sigma square mu ml by 1 by sigma square plus 1 by n sigma naught square. Okay, so I've just multiplied and divided by n. And in this case, if n is infinity, then this and this are going to be close to 0. And again, in this case also, mu map is equal to mu ml. So if you have lots and lots of data, if you have lots of data, if you have a large number of training samples, then ML estimate and the map estimate will be equivalent. So having did all this and having seen, now what can you say about map? What is the, when is a good situation to use map? When should we use map estimate rather than the maximum likelihood estimate?
When we have large data, large amount of data.
When we have large amount of data, or when we have less amount of data? You should use it when you have less amount of data. Because if you have large amount of data, your ML estimate and map estimate will be almost the same.
Yeah, okay, sir.
Okay, so again, I'll tell you one practical use of map. For example, so I told you, right? Where do we get this? Somebody has to give you the hyperparameters, this mu naught and sigma naught square. So one practical way where it is actually used in, like, I think it is now it is all dominated by deep learning, but again earlier in the maybe some 10 years back, if you wanted to use map estimates, what you would do, suppose you wanted to classify, there are some classes, let's say there are 3 classes. Classes are class 1, class 2, class 3, for example, and each class has its own sets of data, data 1, data 2, data 3. Okay, and we are going to assume that it is normal PDF, and you want to estimate the I will just write. You want to estimate the parameter vectors theta 1, theta 2, and theta 3 corresponding to each class. Let's say we want to estimate the map estimates of these parameters of the 3 classes. So one way to use a map estimate is to make a big data set D, which is the union of D1, union D2, union D3. Okay, and for this you estimate the ML estimates of theta, that is for this big data set. Now these will form the prior for theta 1, theta 2, theta 3. So one thing you can, similar to what we did earlier, we can assume that if it is mean and variance, we can assume that the variance is the same for all the 3 classes. and the means are going to be different for each of the 3 classes. So the hyperparameters are now going to be the mu naught, which you will use is the ML estimate of the big data set. The variance is going to be the same variance for each class. I mean, that is one way to estimate. If you want, you can have each class to have its own mean and its own variance, but that will require you to estimate more number of parameters. So one reasonable assumption is to assume that the variances across all the classes are the same, and the means for each class is different, and you can the distribution of those means has the distribution equal to the ML estimate of the mean of the D of the complete set of data. So this you can use to give you to approximate a map estimation of the each of the theta 1, theta 2, theta 3. So this was a practical way of using this. In fact, if you have time, you can even do this in your assignment. But that first assignment itself, it will give you, even without, even by just using the sample mean and sample variance itself, you will get pretty good accuracy for the non-linear data. But for the linear data, and if you try it for the non-linear data, maybe a map estimate will give you slightly better classification results. Okay, so this was a practical application of map. So you can, so when you do it like this, you will have more data. When you will have more data. I mean, suppose you have only 100 examples in each class in the training data. So when you pool the data like this, you will have 300 examples, and so you have more data. And that when you estimate the maximum likelihood estimates with more data, you will get a better estimate. And once you get the ML estimates, you can consider those ML estimates as the hyperparameters for the individual map estimates, and that is what you're going to do. That is what you're doing here. Okay. Yeah, so that is all. I wanted to start something else now, but today there is no time. Let us, hopefully we can, I don't know, next class tutorial. I'm planning a tutorial on tomorrow. Again, that depends on whether you guys can come here in person. If you cannot come in person, then we will probably not do it. Okay, anyway, I'll send you details over email. But tomorrow, come ready for a tutorial session. Okay, and in this situation, I don't know how the midterm exams will happen if the landslide keeps happening, but we'll see. That is not up to us to decide. Okay, any questions on what we covered today?
No, sir.
Okay, then I think we will stop. CS669, I will send you an email about the exam. Okay.
Okay, sir.
Okay, then. Thank you.